quadratic from first principle. A quadratic is y equals ax squared. The squared is to power of 2, and that's the highest exponent, and that's what makes it quadratic. Y equals ax squared. The squared is what makes it quadratic. The highest exponent is 2. Now we've got a quadratic curve here where x is greater or equal to 0. This is 0 here. Now to find the gradient, we can pick a point here and a point there. When we pick that point, that would have a coordinate of x and a coordinate of y. This will have a coordinate of x as well, but not just x plus dx. And this will have a coordinate of y plus dy, right? That's what we normally do. So we say y plus dy. And the coordinate then will be x plus dx, comma, y plus dy. But then when we join the line, it's not a tangent. You see, it's not a tangent. It's just cutting the curve. And that gradient is not appropriate gradient because the gradient on a curve is changing. It's a variable gradient. Every point on the curve has a different gradient. And we've picked 2 points on the curve, which means that gradient is different from that gradient, so this line is not going to be true. So what we have to do is try and find a tangent and then keep minimizing the gradient to a smaller and smaller point and have a proper tangent here. So for instance, if I pick another point here, so that point will be a proper tangent now, see? That point will have a gradient. So if I draw that point down, so that will be the x here. And it will have a very small difference between that and the next one along to find the tiniest gradient on that one. And this tiniest bit, really small, actually smaller than that. So that will always, we don't call it the x anymore because the x is quite bigger. We don't call it the x anymore because the x will be slightly, you can see that will be on this one here, this will be the dx here. So that will be dx. So that's the green one here is dx because it's from there to there. And this height here will be dy. But we're not doing that anymore. We're just doing the tiniest bit. So the tiniest of all. So maybe even smaller than that. So we don't then call it, so if this is x here, so that's x. And the tiniest bit here, we call that x plus, instead of calling it dx, we call it delta x because it's so small. And this one here this is y here. So that's a new y because it's a new y now. So that's y. And the tiny one here will be a new small change, so that'll be y plus. Instead of saying dy, we say delta y. So that means it's such a tiniest small difference. And that's what we're working on now. So the new coordinates we'll be working on will be x plus delta x, comma, and y plus delta y. So that will be the new point we'll be working on. That. So the gradient is small and small and small. And that's the method we're going to apply to curve because we want it to be the gradient has to come to the point that it becomes a tangent at the curve. At the curve, it has to be a tangent to the curve because each point along the gradient is variable. So that gradient is different from that gradient. So now, to work out what's going on, we now have our equation is y equals ax squared, right? And then that's this point here. So that point here is y equals ax squared. And this point here, the tiniest increase, will then be, for that, we're going to write y plus delta y equals a open bracket x plus delta x, because that's, if this is y plus delta y, then the coordinate here, the x will be x plus delta x squared. So what we now need to do is expand this bit here. So we have to do a bit of expansion, and expanding that would be a, right, so that would be x, so let me just use square bracket to keep it easy. So that would be x squared plus 2a delta x plus delta x squared. So that's the expansion there. So I've just expanded x plus delta x times x plus delta x. If you multiply them, or you expand the bracket, this is what you get. Now, with that done, and that's basically y plus delta y. Remember, sometimes the delta x is called h. So that's another word people use for delta x. They use h instead of delta x. So they'll call this one x plus h. I'm just sticking to the delta x because it's classic. It's a, you can change all the delta x to h. And so next is, let's just draw this line down. And now I'm going to carry on with the expansion. So I'm going to multiply out with the a. Oh, that way, by the way, that's x, not a. Excuse me. So that's the x. So it's 2x delta x. Right, so carry on with the expansion now. So I'm going to y plus delta y equals ax squared plus 2ax delta x plus a delta x squared. That squared is for delta x squared. So let me just put a bracket there, and that's what that meant. And the squared here is for delta x. Now, so what we now need to do is take the y to the other side. So delta y equals a x squared plus 2a delta x plus a delta x squared minus y. So what I've done is I've taken the y from there to there. I've subtracted y from both sides. Delta y equals, so y is ax squared. So that's ax squared plus 2a delta x plus a delta x all squared minus ax squared, because y is ax squared. Well, minus 2 plus 2 minus 2 will cancel out, right? So that's the same thing here. And then we have delta y equals 2a delta x plus a delta x all squared. Right, so now what we need to do is divide both sides by delta x, because that's the goal here. Delta y over delta x equals 2a delta x plus a delta x all squared. That's divided by delta x, and that's divided by delta x. Well, delta x cancels delta x. You're left with one delta x here. So you get delta y over delta x equals 2a plus Along the road here, I've just missed out x. I don't know why I keep missing out the x. So that's x there, that's x there, that's x. You can see the x is missing out. Just decided to disappear. Okay, now it's come back again. So the x is still here. So that's important. Because there was an x here. When we do the expansion, there's ax, so that's ax. And for some reason, I just missed it out. And it's back in there. Right. Plus a delta x, because if you cancel delta x from the squared, you just get one delta x. Now this comes the big in the limit situation. Now, because it's so small, and what we want is the change, the delta x has to be so small to the point that it just looks like a tangent to the curve. And therefore, we have to say in the limit, yeah, where delta x has to change to become 0, right? At that point, delta y over delta x can then equal dy over dx, which then equals to 2ax, which then equals 2ax plus, well, the x is now 0 plus a times 0. And therefore, now we can call it dy dx because the limit says it's so small that now we can get dy dx. Therefore, now we have the authority to use dy dx. Otherwise, you're not allowed to use dy dx. You have to use delta y over delta x until you've done your limit. In the limit, you have to say delta y over delta x will be equal to dy dx as delta x tends to 0. As the difference here, that difference is delta x, which sometimes is called h, as that comes to near 0, but not 0, near 0. And that's what that implies. And therefore, then we can say dy dx. So we can say dy over dx equals 2ax. So that's the differential of y. So when you have a function that says y equals ax squared, the y dx will be 2ax. The 2 will come down here, and that's 2ax, and that's the derivative of y equals ax squared. So this is what the books are using. So let's just draw that one down. Some books are using this method. Derivative. Whenever you do derivative, we can say y is also f of x. And for derivative, the y dx is also called f of dash x. That's for first derivative. And for the second derivative, just to put that in, second derivative, and that will be f of dash dash x. So I just thought I'd put that in there. So that's how you write that. Sometimes it's also written as y dot. Sorry, that's y. Excuse me. That equals y dot. That's the derivative. And you can guess what the derivative of the second will be twice. It's going to be y dot dot. So that all means the same thing. The 2y dx squared equals f dash dash. That means twice the derivative of with respect to x, or you might say y dot dot. That means it's done it twice. So the what people do, right, is f of x, f dash x, that's dy dx, equals to ax squared. In fact, let me just write it this way. We tend to write this open curly bracket, f of x plus delta x, right, minus f of x and divided by, some people write h, but delta x. Delta x is h, just to say delta x is h. So you might see h there, and then you close the square, your curly bracket. And that's what you write. But then you have to write the limit, and that is delta x tend to 0. If we put it back in there, so this would be ax squared. So that's what that is. Minus, and this one here will be a open bracket x plus delta x squared. So that's what this one is, and that's that one. And we've done that here anyway, so that's what we've done here. We're doing the same thing as we go along. And then you then divide it by the x, so that's the division by the x here. And then the limit is our limit here. That gives you the authority to now call that dy dx. That's what that meant. So it's the same approach to solving the dy dx.